morning, ladies and gentlemen. I have the pleasure of sharing with you our ABB solution that actually saves lives, money, reduce your downtime, saves your equipment in the event of an electric fault. We've all had the excitement of seeing things being blown up this morning from a very safe distance. What if that distance is not there? If you're close to the switchgear, what's going to happen? What are the results of why do these things happen? Why do electric arc faults happen? Okay, some of the reasons for these things happening, you can have human error, mechanical, bad mechanical connections, mechanical faults, pollution, rodent running into the board, etc. But what's interesting to note is that the percentage of arc faults that generally happen, the reasons why, you'll find that about approximately 25% is without the operator being near the switchgear, about 10% with the operator in front of a closed switchgear, but 65% is when the operator is actually working on the switchgear. So that statistic is actually very interesting to note. This is generally what happens when this phenomena occurs. Generally, before all that occurs, your lungs would have been burned out by the time you inhale all the toxic vapors. So based on IEC 61641, electric arc fault containment, it states that the arc fault contained switchboards generally have to contain the arc fault for up to about 300 milliseconds because they expect your short circuit protection relay to kick in by then. Now, with the arc guard system, we can actually reduce that time, that tripping time, to about 30 to 45 milliseconds. So it's interesting to note, based on this timeline against the energy that's being plotted, if you look at anything after 50 milliseconds or 100 milliseconds and above, you start seeing cable fire, copper fire, and sheet metal fire. So what we're saying is with the TVOC2 arc guard system, we can actually trip the breaker within 30 to 45 milliseconds. So as you can see, this is an incident without the TVOC. Now, before I play the next slide, please use the abilities of your peripheral vision and take note of the time between 30 to 50 milliseconds and the video that occurs on the right-hand side, the actual you'll see the arc being slowly extinguishing because of the tripping of the circuit breaker. So look at the way the time, it's up to 30 to 40, and you can see the slow extinguishing of the arc. So that's what we're talking about. Okay. How it works, it's a very simple system. With the light sensors and the fiber optic cables, that actually detects if an arc occurs, it would detect the arc, and it would send a signal to the TVOC unit. The TVOC unit would then send a signal to the breaker to trip the breaker. It's that simple. Okay. Now, basically, what is the radial sensing of the sensors? They operate up to about 3 meters. It's a radial optical sensor where there is a slight bend at 30 degrees angle. That radial sensing would be about limited to about 1.5 meters. Now, the good thing about these fiber optical cables and the detectors, they're prefabricated at the factory, so you actually reduce the risk of calibration. They're fabricated between, you can have a 1 meter length, 2, 4, 6, 8, all the way up to 60 meters in length. And because it's fiber optic, you have immunity against electromagnetic interference. Okay. Generally, the detectors, they detect light. Sometimes people will say, how about in the events of if I were to take a picture of the board and that's going to set off the tripping of the breaker or set off the T-VOC and the tripping of the breaker. That is true. So that's why we have a current sensing unit to match. So you've got light and current, and you need these two conditions to be able to trip the breaker. Okay. Where you can actually install the sensors. Generally, it will be in the horizontal busbar compartments, the dropper busbar compartments, the incoming cubicle, and the outgoing as well. That's generally where you would put your light sensors. If you just pay attention to the table below, we've got two sets of tripping options. One is with the shunt trip release, which gives you a tripping time of 60 to 75 milliseconds before the breaker trips. And the other one is actually with our PR120K, which is a signaling module. That is actually integrated into the breaker. So you actually get a much shorter tripping time, which is 30 to 45 milliseconds. Because it is integrated with the breaker, the protection relay actually controls the tripping of the breaker directly. Hence, you're able to achieve 30 to 45 milliseconds. Why short circuit is not enough? There are a lot of applications out there that require selective protection, where you generally have upstream, downstream breakers tripping. So generally, you'd like to isolate the fault, and you'd like the breaker that's closest to the fault to trip. Now, in cases like this, where you have to set different levels of currents and different time delays, there will be a case where you may have to set your upstream breaker or your main circuit breaker, say, for example, at 70 milliseconds. Now, that may not be enough to trip your breaker in the event of an arc fault. That is the reason why you should have an arc guard system. This is just a typical schematic of how the T-VOC works. In this case, it is basically just monitoring a one switchboard where you've got the upstream and downstream breaker. In this case, if detector 1, which is the yellow lines that you see, which is closest to the upstream breaker. Now, if detector 1 detects an arc light, and the current sensing unit also operates to say there's an anomalous current, then you have the upstream breaker tripping. Now, if there were any other of the detectors downstream of the second breaker, then the second breaker would trip. In this instance, you have two boards where you have a bus coupler. So basically, you're monitoring two sets of bus bars. So again, similarly, if the first detector 1 closest to the upstream breaker detects a light, and then you have current conditions being, yes, it's an anomalous current, then the upstream breaker would trip. And for detectors 3 and 4, that would trip the second breaker after the upstream breaker. And for the bus coupler breaker, then that would trip if the 8 and 9 detector 8 and 9 senses a light and you have the correct anomalous current conditions. So this is what, in a nutshell, what the ARC monitor consists of. So you have 3 solid-state tripping contacts. What does that mean? That means you can trip 3 breakers differently at different times, depending on where the fault occurs. Okay, you have 2 changeover trip signals. Now, these 2 trip signals actually allows monitoring. So you can actually have a trip signal going to, say, a PLC, and another trip signal going to, say, a SCADA monitoring system or your DCS monitoring system. So you've got up to 2 changeover trip signal relays. And of course, the T-VOC also comes with a self-supervision relay, which tells you if your T-VOC has any issues. Say if the power supply is off or down, or if there are some diagnostic issues with the T-VOC. So that self-supervision relay would actually trigger off an alarm to say, hey, there's something wrong with your T-VOC, go check it out. 2 current sensing inputs, that would be for the current sensing unit. Now, there are 2 of them there. It actually allows, again, like in that situation where you have a bus coupler, you're monitoring two switchboards. So you can actually have up to 2 current sensing units being connected to the one T-VOC unit. 1 current sensing output, you can actually have a signal sent from this current sensing output between TVOC to TVOC. So if you have two TVOC units monitoring two different switchboards, the second TVOC would then know that, look, there is a fault in one of the switchboards. Okay? Your detector, your sensors, you can have up to 30 sensors. The typical standard unit comes with 10 sensors. So you can actually have an extended expansion module, but it's integrated with the TVOC unit, so it doesn't take any additional space in the board. Okay, reliability. So we've got more than 35 years experience. It's certified to functional safety, SIL2. It's got its own self-supervision, alarm, etc. It's prefabricated. There's no risk of calibration. There's immunity to EMI. And basically, there's no software, so you don't have to worry about, electronic issues. Flexibility, HMI, what's that? That's human-machine interface module. You can actually have up to 2 of these HMI modules, so one can be placed with the product. The other HMI can be actually on the front of the door panel. You can have up to 30 detectors, as mentioned, so you can actually, you'll be looking at probably up to, usually we'll look at 2 sensors per panel, so you're talking about 15 panels approximately. Simplicity, it's as I said, it's a very simple unit to use. Everything is easily programmable. It's a touch screen, simple menu operated. This just gives you an idea of the applications of the TVOC's capability. As you can see, it's not just low voltage. It can be taken up to high voltage. It just depends on the complexity of your applications. And we've had several occasions where we've got medium voltage applications using the TVOC system. So we work very closely with our colleagues in the medium voltage side, and they find that with the TVOC, it's a lot more cost competitive compared to using the arc guards on the medium voltage applications. Okay. So why should we use it? Well, it saves lives, saves your equipment, reduces your downtime, and in general, saves costs. Thank you very much.